Welcome. Today, we're diving into the absolute fundamental rules of the universe. We're looking at the ultimate rulebook that governs literally everything around us, from the steam rising off your morning coffee to the life cycle of stars. It's the cosmic game of energy, heat, and order. We're talking about thermodynamics, and we're going to break it down with a clear, structured look at exactly how these invisible forces shape our reality. To get this right, we're using an incredible source, Statistical Physics of Particles by MIT professor Marin Kardar. Now, look, this is a graduate-level physics textbook. It's dense, it's mathematically intense, and yeah, it's pretty brilliant. But hey, don't worry about getting lost in the weeds. Our goal today is to extract the core building blocks of thermodynamics from his work. We're going to pull out the foundational concepts and translate them into a clear structure, so you can see exactly how the mechanics of the universe operate. Okay, let's dive into this. Here's our roadmap. We'll kick things off with an introduction, then hit the zeroth, first, and second laws. After that, we'll check out the Carnot engine, and finally wrap it all up with entropy.
Section 1, Introduction to Thermodynamics. Setting the playing field.
So before we learn the rules, what exactly are we looking at here? Well, in thermodynamics, we really need to zoom out. We step away from the totally chaotic, unpredictable movements of billions of tiny individual particles. Instead, we look at large, idealized systems, macroscopic systems, and we measure them using big-picture stuff like pressure, volume, and tension. And crucially, we do this when the system is in thermal equilibrium. That just means its properties aren't wildly fluctuating while we're watching it. We're keeping our eyes on the big picture. Section 2, the zeroth law, defining temperature. You know, it's actually called the zeroth law because physicists only realized how fundamental it was after the first and second laws were already a done deal, so it had to literally jump to the front of the line. It establishes something we take for granted every single day. The law says that if two systems, let's call them A and B, are separately in equilibrium with a third system, C, well, then they have to be in equilibrium with each other. I mean, it sounds like basic logic, right? If A equals C and B equals C, then A equals B. But in physics, this transitive property is an absolute game changer. It's the only reason empirical temperature and thermometers themselves can actually exist and work. Now, what's really interesting is how systems A and B interact with C through what we call diathermic walls, basically walls that let heat pass through. Because A and B both reach a state of balance with C, they're balanced with each other. This physically shows us that transitive equilibrium in action. And it's huge because it lets physicists define a universal equation of state for temperature. So instead of just relying on how hot or cold something feels to us, we can actually anchor our temperature scale to a universal physical constant, like the triple point of water. That's the exact, precise condition where ice, liquid water, and water vapor all perfectly coexist. Section 3, the first law, conserving energy. All right, so with temperature officially defined, we can shift our focus to the total amount of energy packed inside a system. Enter the first law. This rule dictates that the amount of work required to change the state of an isolated system depends only on its initial and final states. It totally doesn't matter how it got there. And this gives us two absolutely crucial concepts: internal energy and heat. The big takeaway: energy cannot be created out of thin air, and it definitely cannot be destroyed. Any change requires a fixed, strictly accounted for amount of energy. If you pump heat into a system, that energy has to go somewhere. It's either going to bump up the system's internal energy, or it's going to cause that system to do mechanical work on its surroundings. This brilliantly illustrates just how universal this concept of work really is. I mean, we aren't just talking about pistons pumping in some car engine. Mechanical work just needs a generalized force and a generalized displacement. For a stretched wire, that's tension and length. For a fluid, it's pressure and volume. For a magnet, it's the magnetic field and magnetization. So you have these completely different physical systems with totally different properties, but the exact same thermodynamic math applies to calculate the mechanical work being done. How cool is that? Section 4, the second law, heat's direction. Okay, so the first law says energy is conserved, right? But it actually doesn't tell us which way that energy naturally flows. This practical problem is exactly what birthed thermodynamics back in the Industrial Revolution, when engineers were desperately trying to build better steam engines. The second law is best understood through two incredibly strict, famous statements. First, Kelvin's statement. This declares that there is no possible process where the only result is the 100% conversion of heat into work. You're always going to lose some heat to the exhaust. Then we have Clausius's statement, which says heat will never naturally flow from a cold body to a hot body unless you apply external work. Together, these rules mean the universe strictly forbids perfect, 100% efficient engines, and it definitely forbids perfect refrigerators. No magic machines allowed. Professor Kardar walks through a really fascinating logical proof for this. Think about this mini narrative. If you somehow managed to build a magic machine that violated Clausius, like, say, a refrigerator that moved heat from cold to hot using zero energy, well, you could just hook it up to a standard engine, and boom, suddenly you'd be converting 100% of your heat into work, which completely violates Kelvin. Breaking one perpetual motion machine rule instantly breaks the other. The universe simply will not let it happen.
Section 5. The Carnot engine.
Real engines are messy, right? They lose heat, there's friction, it's a whole thing. So physicists needed a way to test the absolute theoretical limits of the second law. Enter the Carnot engine. This is a purely theoretical construct. It's an idealized, reversible, cyclic engine where all the heat exchanges happen at exactly two temperatures, a hot source and a cold sink. And because it's totally reversible and runs in a perfect cycle, there's zero friction, no wasted dissipation at all. It is literally the thermodynamic equivalent of frictionless motion. It represents the absolute maximum efficiency any engine could ever possibly achieve in our universe. So, the crucial point is how we actually measure this efficiency. For an idealized engine, it takes in a very specific amount of heat from the high-temperature source, does a certain amount of work, and then just dumps whatever heat is left over into the cold sink. The efficiency is simply the work done divided by the total heat it took in. And the beauty of it is, if you run the whole thing in reverse, it becomes an idealized refrigerator, using work to pump heat from that cold sink straight back up to the hot source. To see exactly how this perfect machine operates, we can look at the closed loop of the Carnot cycle for an ideal gas. The solid lines represent isotherms. These are paths where the temperature stays exactly the same while the engine exchanges heat with the source or the sink. Then, those dashed lines are adiabatic paths. That means the gas is expanding or compressing completely insulated from the outside world. Zero heat escapes, zero heat enters. By cycling through these perfect curves, the engine extracts the maximum possible work. It's like a perfectly choreographed dance. Which brings us to a massive rule, Carnot's theorem. It simply states that absolutely no engine operating between two reservoirs can ever be more efficient than a Carnot's engine. Why is that such a big deal? Because it establishes a universal maximum efficiency limit, a limit that depends entirely on the temperatures of the hot and cold reservoirs, and not at all on the gas, the metal, or the mechanics you use to build the thing. Because of this brilliant realization, physicists were finally able to create a true, absolute thermodynamic temperature scale that is completely independent of any specific physical material. Section 6, Understanding Entropy. Okay, so we've defined temperature, we've conserved energy, we've figured out which way heat flows, and we've found the absolute limit of efficiency. Now we build to the real climax of this explainer, where all these rules combine to reveal one final, ultimate state function. We start with Clausius's theorem, which is just a massive mathematical milestone. It says that for any cyclic transformation, the integral of the heat supply to a system, divided by its temperature, is always going to be less than or equal to zero over a complete cycle. The only time it ever equals exactly zero is if the entire cycle is perfectly reversible, like our trusty Carnot engine. If there's even a tiny bit of real-world inefficiency, any irreversibility at all, that value drops right below zero. Let's move to and see how this builds into the concept of entropy, which we represent with the letter S. Because a perfectly reversible cycle equals exactly zero, the math tells us that the integral of reversible heat divided by temperature is completely independent of the path taken. It literally only cares about the starting point and the ending point. That means it is a fundamental state function, just like pressure or volume. Essentially, entropy acts as the specific displacement that is conjugate to temperature. And that leads us right to this. Professor Kardar actually calls this likely the most fundamental and useful identity in all of thermodynamics. It is just incredibly elegant. The change in internal energy equals temperature times the change in entropy, plus the sum of all mechanical work done on the system. It perfectly unites internal energy, temperature, entropy, and mechanical work into one single, beautifully unified equation. The entire rulebook of the cosmic game captured right there. But the ultimate consequence of all this math? It's profound. In the real world, changes are almost never perfectly reversible. Irreversible changes always increase a system's entropy. Therefore, in any isolated adiabatic system, meaning a system where no outside energy can enter or leave, spontaneous internal changes are constantly going to drive an increase in entropy. It is a one-way street, folks. The system will inevitably march forward until it attains a maximum possible value of entropy, ultimately reaching a final state of complete static equilibrium. Which leaves us with a truly chilling, awe-inspiring question. Our universe is, as far as we know, a closed, isolated system. If the laws of thermodynamics strictly dictate that the universe is constantly marching toward maximum entropy, what happens when all spontaneous internal changes finally just stop? What happens when all heat is perfectly evenly distributed, no more work can possibly be done, and maximum equilibrium is reached? It's an incredible realization about the ultimate thermodynamic fate of literally everything that exists. Thank you so much for joining me on this exploration. I hope this explainer gave you a clear, powerful understanding of the invisible rules governing our cosmic game. Keep questioning, keep learning, and I'll catch you next time.